In the next couple of units, we'll be determining steady-state responses to sinusoidal inputs. For linear systems, this converts the governing differential equations into algebraic equations, which is a huge savings in effort. In fact, this benefit is the main reason why engineers like to analyze linear systems, even to the extent of pretending that a nonlinear system is linear. The sinusoidal steady-state response is the system's response to a sinusoidal input as time goes to infinity. As time goes to infinity, the homogeneous solution dies out, so we're going to be looking only at the particular solutions of differential equations. These solution approaches are appropriate for any order of system, whether it's first, fifth, or higher orders. Before I get into sinusoidal responses, I want to put this problem in context with the other differential equations we've been solving. So far, we've considered the natural response of a system and the system's response to a constant input. These have both required the homogeneous solution. For the natural response, we need only the homogeneous solution, and for the step response, we needed both the homogeneous solution and the particular solution to a constant forcing function. We've also restricted our solutions to only first and second order systems. Keep in mind that it was mostly the homogeneous solution or natural response that was affected by the system order. If we're only interested in a particular solution to a constant input, the system order doesn't really make much difference. We replace capacitors with open circuits and inductors with short circuits and solve the circuit. We can do that same process with any order circuit if the input is constant and we're only interested in a particular solution. In the case of a sinusoidal input, the particular solution is not a constant, so the solution approach is more complicated, but we still don't need to worry about the initial conditions and the associated homogeneous solution. Next, I want to briefly talk about sinusoidal functions themselves. You're probably familiar with these types of functions already, but I do want to make sure I've reviewed the basic terms and concepts relative to these functions. The form that I'll use for a generic sinusoidal function is this. Y of t is equal to y sub p, which is just a number, times the cosine of omega times time plus a phase shift theta. This is what a typical sinusoid looks like. I'll explain in a later video why I prefer always using cosine functions over using both sine and cosine functions. For the moment, I'll just point out that a sine function can be written as a cosine function with an appropriate phase difference. The amplitude or peak value of a sinusoid in this form is y sub p, which is the maximum value the sinusoid reaches. Amplitudes of sinusoids are also sometimes indicated by what is called their peak-to-peak value, which is the amplitude difference between the highest and the lowest value the sinusoid reaches. For a sinusoid of this form, yp will be 1/2 of y peak to peak. In other cases, where the average value of the function is not 0, this won't be true. A non-zero average value is called a DC offset. For now, we'll be working with sinusoids that have 0 DC offset. The phase angle, theta, just shifts the sinusoid in time. That's why cosine and sine functions are interchangeable. A sine function is just a time-shifted cosine function. For example, this sinusoidal signal is just a cosine which has been shifted to the left by theta over omega seconds. Theta should have units of radians, but is often expressed in degrees. To convert from radians to degrees, multiply by 180 over pi. Finally, I'll talk about the frequency of the sinusoid, omega. Omega gives the number of radians of phase difference the sinusoid experiences in 1 second. Since there are 2 pi radians in 1 cycle, the time between peaks of the sinusoid is 2 pi over omega. The time period between peaks is also called the period, abbreviated as a capital T. An alternate unit of frequency is cycles per second, or hertz, and is usually represented by a lowercase f. The period is just the inverse of the frequency in hertz. Now let's talk about the steady-state response of a system to a sinusoidal input. The steady-state response corresponds to the particular solution of the differential equation governing the system, which has the same form as the input. For a sinusoidal input, the output will be a sinusoid with the same frequency as the input sinusoid. However, the amplitude and the phase angle of the output sinusoid can be different from that of the input sinusoid. So if I apply an input with an amplitude A, a frequency omega, and a phase angle theta, the output will have the same frequency, omega, but may have a different amplitude, B, and a different phase angle, phi. One important term relative to a sinusoidal response is the system's gain. The gain is just the ratio of the output amplitude to the input amplitude at some frequency. For this example, the gain is B divided by A. Another important parameter relative to systems is the phase shift. This is just the time delay between the output and the input sinusoids converted to an angle. Now let's summarize these concepts a little bit more graphically. In block diagram form, I have a linear system with some input and some output. We start applying a sinusoid to the system at time t equals 0 as shown here. The output might look something like this. The system is initially relaxed, so the output is 0 before time t equals 0. The system responds to the input and goes through a transition period due to the homogeneous solution before becoming sinusoidal, which is its particular solution. The output as time goes to infinity is a sinusoid with the same frequency as the input. The particular solution has the same form as the forcing function. However, the amplitude of the output might be different than the amplitude of the input, and the sinusoid may be shifted in time relative to the input. The period of time affected by the homogeneous solution is called the transient. Once the transient solution dies out, the particular solution is left, which is called the steady state response. In the case of a sinusoidal input, the steady state response is a sinusoid. Another important thing to remember is that this discussion is relative to a single sinusoidal input at a particular frequency. The system will typically respond differently at different frequencies, so that the system gain and phase difference will vary with frequency. Next, I'll do a demonstration with a physical system to illustrate sinusoidal steady state responses. This is the system I'll use to demonstrate sinusoidal signals and gain and phase of systems. I have a motor down here with an offset cam. As the cam turns, the top of this string moves up and down sinusoidally. As I increase the motor speed, that frequency increases. I'll choose the displacement of the top of this spring as my input to my system and the displacement of the bottom of the spring as my output from the system. At low motor speeds and low frequencies, the top and bottom of the spring are moving the same. They're both going in the same direction at any given time, so the phase difference introduced by the system at low frequencies is 0. Their amplitudes are also the same. The bottom moves the same amount as the top does, so the gain is 1. Now if I increase the voltage to the motor and increase the frequency of the input, the bottom of the system will go through an initial transient, but it'll eventually become sinusoidal again once it gets to the particular solution. At a somewhat higher frequency, the amplitude of the input is still small, but the amplitude of the output has gotten huge. So the output has a much higher amplitude than the input has, and the system gain is very high at this frequency. Also, the top and the bottom of the spring are no longer going in the same direction at the same time. When the output displacement is at its maximum, the input starts going up. So the system is introducing a 90-degree phase shift between the input and the output. At even higher frequencies, the displacement of the output has gotten small again, so the gain of the system has gone back down to a low value. The motion of the top and the bottom of the spring are now in opposite directions. So the system's introduced a 180-degree phase shift between the output and the input. Now let's look at the math associated with doing a sinusoidal steady state analysis. At this stage, I'll skip a lot of the details. I just want to present the general idea in this video. Here's a simple RC circuit. I have a voltage source that's applying a sinusoidal input, and I want to determine the voltage across the capacitor, Y of t, as time goes to infinity. The source has an amplitude of 3 volts, a frequency of 50 radians per second, and a phase angle of 20 degrees. This is the differential equation governing the system. This term is the voltage across the resistor, this is the voltage across the capacitor, and this is the input voltage. I'm just looking for the particular solution, and the form of this solution will be some unknown amplitude b times the cosine of 50t plus some unknown phase angle phi. The solution approach is similar to that for a constant input, except in this case the solution's not a constant and the derivatives don't become zero. The derivative of a sinusoid is another sinusoid. If I take the derivative of y of t and plug it in here, I get this expression. I need to solve this for the unknowns b and phi. So I'll need to apply some trigonometric identities, convert this to two equations and two unknowns, and solve the equations to get my unknowns. This process is fairly painful and gets considerably more painful quickly if the circuit's more complicated. In particular, increasing the order of the differential equation makes this solution a lot more tedious. As I've said, I don't want to go through the details. I just want to give you the basic idea of the solution approach. The basic idea here is that working directly with sine and cosine functions is difficult. So let's see if we can come up with a simpler approach. Since engineers always want to make the math as easy as possible, let's see if using complex exponentials will make our lives easier. In the second order system response unit, I pointed out that cosines, sines, and complex exponentials are all types of sinusoids. Per Euler's equation, the cosine of some angle, psi, can be represented as 1/2 e to the j psi plus e to the minus j psi. We can generalize this by making the angle a function of time. That means that a times the cosine of omega t plus theta is equal to a e to the j omega t plus theta plus a e to the negative j omega t plus theta over 2. If we factor out the e to the j theta, we get a e to the j theta e to the j omega t. A is the amplitude of a sinusoid, the frequency is omega, and the phase angle is theta. Complex exponentials, sine, and cosine forcing functions all have the same effect on the particular solution to a differential equation. If the input is a complex exponential with some frequency omega, the particular solution, or the steady state response, will also be a complex exponential with frequency omega. Now let's take a look at our previous example if we use a complex exponential forcing function. Let's see how to analyze this circuit if the input is a complex exponential. This complex exponential has the same amplitude, 3, phase angle, 20 degrees, and the same frequency, 50 radians per second, as the function on the previous slide. I want to point out that this signal can't be created physically. It's strictly a hypothetical mathematical construct. We'll worry later about whether this one can actually help us with the analysis of a real circuit. The differential equation governing the circuit hasn't changed, except that the right-hand side is now a complex exponential. The particular solution has the same form as the forcing function, so it becomes a complex exponential with an unknown amplitude b, a frequency of 50 radians per second, and an unknown phase angle phi. Plugging this function into this equation gives us this. A wonderful thing happens in this equation. The e to the j50t terms all cancel out, which leaves us with a function that doesn't change with time. It's just a simple garden variety algebraic equation with some complex numbers in it. This is a huge advantage. We've converted a differential equation to an algebraic equation. If I factor out the b e to the j phi, from this equation I get this. We can easily solve this equation for b times e to the j phi by doing arithmetic with complex numbers. Using complex exponentials in steady-state sinusoidal analysis saves a huge amount of effort if you're proficient in complex arithmetic. The next video provides a review of complex numbers, complex exponentials, and complex arithmetic.